Welcome everyone. Today we'll be discussing DDoS mitigation in 5G with a focus on our novel solution, Dawn, and its integration of SDN and machine learning capabilities. This research has been conducted at the NYU Tandon School of Engineering. In this session, we'll delve into the security challenges 5G faces due to DDoS attacks. We introduce our solution, Dawn, that's positioned at the edge of the core network, and we discuss its workflow and setup. We believe Dawn, with its unique capabilities, can be a game changer in the 5G plus era. "5G, as many of you know, represents a significant leap in wireless technology. With enhanced connectivity, faster data transmission, and support for new applications, it's the next big thing. But with these advancements come significant security vulnerabilities. 5G has revolutionized connectivity, but with it comes amplified threats. The newness of 5G means uncharted vulnerabilities, and its different architecture means traditional defenses might falter. We're contending with faster data transmission, more devices, and a greater emphasis on edge computing, all of which can increase the attack surface. DDoS attacks are not new, but in the 5G landscape, they have become more potent. These attacks exploit 5G network protocols, aiming to disrupt and even halt network services. Many of these very beneficial technologies, such as direct mode communications, which allows devices to communicate directly with each other without relying on base station, and that enhance communication in areas without network coverage, all the way to vehicular communications, which are dedicated communication systems for vehicles, enabling information exchange between vehicles and between their infrastructures for improved traffic management and safety. Each of these technologies contributes to the versatility and capability of 5G networks, but they also introduce potential vulnerabilities that can be exploited by DDoS attacks, thereby necessitating robust security measures. When a DDoS attack is launched, it targets various network segments. The result? The server's processing capacity and bandwidth gets strained, making services slow or completely inaccessible. With 5G's implementation, the enhanced mobile broadband and massive machine-type communications can send large data volumes. This amplifies the DDoS attack potential, presenting immense challenges for cybersecurity experts. Let's briefly delve into the different types of DDoS attacks. A significant player in executing these attacks are botnets, large networks of compromised devices. And here's a challenge we often face in traditional setups. While we can confirm if the user is genuine, verifying the authenticity of the traffic they send is difficult to figure out. Volumetric attacks aim to consume all available bandwidth of the target's network connection. The attacker sends an overwhelming amount of traffic, intending to exceed the capacity of the victim's infrastructure. It's an overload by volume. Let's discuss the mechanics of the major volumetric attack. UDP floods. Attackers send a massive number of user data protocols, UDPs, packets to random ports on the victim's system. As the system tries to respond to each packet and fails, it gets bogged down. Another type is DNS amplification, where the attackers send DNS query requests with the spoofed IP address of the victims to OpenDNS servers. These servers respond with a much larger data amounts, overwhelming the victim's response resources. There's also ICMP ping floods. Attackers flood the victim with ICMP echo requests or ping packets. The victim must process each packet, exhausting resources. We see a pattern. Protocol attacks exploit the standard procedures for establishing, maintaining, and ending connections. The SYN flood is a classic example. Attackers initiate a connection but intentionally don't complete it, leaving the server's resources tied up, waiting for a response that never comes. Application layer attacks target specific applications rather than the whole infrastructure. The HTTP flood simulates legitimate HTTP requests, but in vast quantities. The server sees them as genuine users and exhausts its resources trying to respond. In essence, attackers exploit the server's trust. Low and slow attacks are not about volume, but duration. They consume a small amount of resources over an extended period, flying under detection radars. The idea is to engage the target system with legitimate looking requests, but at intervals and patterns that slowly consume resources. One type is with a slow Loris. It opens many connections to the server but keeps them open as long as possible by sending partial requests. The server waits for each connection to complete, which gradually exhausts its resources. There is also Rudy, which stands for Are you ready or are you dead yet? Attackers initiate HTTP post connections and send the actual post data very slowly, byte by byte, keeping the target resources engaged and waiting. As for Sockstress, it exploits vulnerabilities in the TCP connection process. By sending specially crafted packets, it can exhaust the server's available connections, preventing legitimate users from connecting. To wrap up, it's clear that DDoS attacks come in various shapes and sizes. Recognizing and understanding them is the first step in bolstering our defense mechanism. An example of a real-world implication is the VoIP.ms attack. In 2021, a DDoS attack impacted the company VoIP.ms, affecting thousands worldwide. VoIP, or Voice over Internet Protocol, allows voice communication and multimedia sessions over the Internet. VoIP providers, essential for global digital communication, became a prime target for extortion-driven DDoS attacks. VoIP.ms, which is a significant player, encountered these attacks, disrupting their telephony services. Cybercriminals, potentially impersonating the REvil group, escalated the ransom demands from $45,000 to a whopping $4.3 million. The industry faced substantial revenue losses and underscoring the critical need for bolstered cybersecurity. Stakeholders impacted by the VoIP.ms attack include VoIP service providers, their businesses, and individual users, as well as security firms, ISPs, investors, and the broad community, a broader economy reliant on stable digital communication. This event underscored the critical need for defenses like Dawn, which we will discuss, in the 5G era. Our solution might have mitigated such threats. We've looked at several notable research papers during the duration of writing this paper. Propositions on using software-defined networks and network function virtualization advancements, and others proposed algorithms against base station attacks. Some delved into vulnerabilities in software-defined networks using machine learning. Another focused on network intrusion detection system for different network segments. Yet despite their contributions, they don't holistically tackle the 5G DDoS challenge. That's why we need a comprehensive solution. Many solutions fixate on software. Others focus on hardware, but the issue won't diminish unless we focus on both. This rapidly changing landscape of threats and various constraints and handling them demands out-of-the-box solutions. We believe that since technological advancements have increased security threats by allowing bad actors to become more creative and use these tools for their advantage, well, it would and should only follow that we too must use all new breakthrough advancements to improve our existing defenses. The best defense mechanisms should be dynamic, intelligent, programmable, and efficient. Even one might hope that would be affordable, but current solutions in use, to the most part, remain rigid. Understanding the intricacies of existing DDoS mitigation solutions can shed light on their strengths and limitations. Today, we will be examining the formidable trio: Cisco Guard, Akamai Kona Site Defender, and Cisco Secure DDoS Edge. Cisco Guard, placed at the network's backbone, acts as a sentinel by distinguishing between legitimate and harmful traffic patterns and employing methods like anti-spoofing, it offers multi-layer defense that adapts swiftly to emerging threats. It diverts suspicious traffic for analysis. It is able to learn normal traffic characteristics. It handles attacks by using anti-spoofing and statistical analysis. Its protection levels vary from analysis to strong protection, and it also is able to scale and manage multiple zones. Akamai Kona Site Defender offers more than just a firewall protection. Its strength lies in its robust cloud infrastructure, enabling it to simultaneously deflect network layer threats and absorb application layer attacks, all the while keeping applications running smoothly. For traffic diversion, it rejects network layer DOS attacks at the edge and absorbs application layer ones. It learns by utilizing Akamai Threat Research for regular updates. For attack handling, it targets application layer and API-based threats. For protection level, it offers IP controls, custom rule builders, and application layer DOS protection. It also able to scale with Akamai globally distributed intelligent edge platform. As for Cisco Secure DDoS Edge overview, Cisco's Secure DDoS Edge is a testament to foresight, identifying and countering threats inherent to 5G landscape. Be it malicious IoT attacks or GTP tunnel breaches, this system acts promptly. For traffic diversion, it prevents harmful traffic at the 5G edge. For attack handling, it handles threats such as IoT bots and DDoS attacks. For protection level, it is proactive, and it is also ready for massive 5G network traffic. An overview of theoretical strategy for DAWN. So DAWN, which stands for Distributed Adaptive Workflow Network, is our proposed network architecture. It aims to be a formidable defense against DDoS attacks. DAWN's audience isn't just limited to one sector. It's essential for any organization dependent on digital communication, including VoIP businesses, banks, healthcare facilities, and government bodies. Its architecture also caters specifically to servers requiring uninterrupted operations. As for theoretical strategy, a researcher that we covered in our paper, Loha Chubb, who wrote a paper on the threat of DDoS in 5G, posits the need for smarter systems to counter novel DDoS threats. Thus, we hypothesize that DAWN can be the solution for 5G, with hardware preprocessors at the core network's edge and a alert-activated auxiliary software-defined network controlling traffic to those preprocessors. DAWN promises scalability and efficiency. It's designed to streamline traffic, distinguish genuine from malicious packets, and ultimately protect the network's core. Let's dive into DAWN's intricate process. It all begins with the robust main SDN, which constantly monitors for unusual traffic patterns or potential threats. Upon identifying anything suspicious, it instantly sends an alert. This alert acts as a wake-up call to our DAWN SDN, prepping it for action. Now DAWN has two key paths from here. Primarily, it diverts all incoming and potentially malicious traffic towards itself for more rigorous analysis. However, in scenarios where DAWN SDN might be compromised or attacked, an automated backup system springs into action to seamlessly take over DAWN's responsibility, mainly using its preprocessors and NFV functionality. Now, to continue, focusing on the traffic DAWN receives, this traffic is meticulously scrutinized by our preprocessors using a specialized defense algorithm. Each packet is analyzed. Packets identified as safe are whitelisted, meaning they pose no threat, and are allowed to proceed. On the other hand, packets raise eyebrows, get blacklisted, marking them as suspicious. These lists are communicated with the DAWN SDN, which in turn shares them with other active preprocessors and the main SDN for further analysis and machine learning. To continue, incoming whitelist packets, which are green signals, then head towards our load balancing algorithm. Here's where DAWN truly shines. It doesn't just direct traffic aimlessly, it smartly leads the traffic volume and distributes this load, ensuring each packet is processed optimally without causing any service interruptions. Our main goal is efficiency in this design. In essence, from the moment a threat is detected to the final load balancing, Dawn is meticulously engineered to offer powerful network security, ensuring optimal operations and utmost safety. Post attack, Dawn SDN doesn't remain active, but intelligently reverts back to a passive state, conserving resources. Having just walked you through the intricate workflow of Dawn, it's crucial to delve deeper into some of its core components. At the forefront of this is software defined networking. Let's delve deeper into the role of SDN in Dawn. SDN isn't just about directing traffic, it offers an enhanced performance and scalability unmatched by traditional networks. The symphony between the control, data, and application planes is what gives Dawn its edge. SDN is the nerve center of Dawn for several reasons. It offers a real-time adaptability crucial in an era of rapidly evolving threats. Centralization allows for comprehensive network oversight, enabling swift, network-wide countermeasures at the detection of any threat. Acting as the network's conductor, SDN manages traffic meticulously, ensuring seamless flow while isolating potential risks. Furthermore, SDN enables Dawn to integrate seamlessly with existing infrastructure, enhancing security without extensive modification. In short, SDN is Dawn's central nervous system, ensuring network security's health. As we progress, we'll delve into the importance of NFV in Dawn's framework. Network function virtualization, or NFV, you can think of NFV as a liberator. It frees network functions from the confines of hardware. This means more flexibility and scalability, and Dawn leverages this beautifully. Dawn and NFV go hand in hand. Dawn taps into NFV's dynamism to swiftly adapt to threats, supercharging its defense mechanisms. When we combine the prowess of SDN and NFV, we're not just looking at defense, we're looking at adaptive forward-thinking protection. And Dawn NFVs are everywhere, from managing traffic to making intelligent decisions in real time, whether it's in the application layer handling traffic analysis or in the data plane directing traffic. NFVs bolster Dawn's defenses, ensuring our network remains impenetrable. The role of machine learning in Dawn. Machine learning significantly boosts DDoS attack detection in software-defined networks, leveraging algorithms like decision tree, random forest, isolation forest, one-class SVM, and autoencoders. These algorithms excel in real-time threat detection, offering minimal computational load and the ability to evolve alongside incoming attacks. Decision trees and random trees stand out for their accurate threat detection and low computational demands. They are pivotal in creating a dynamic, responsive mechanism within SDNs. Neural networks are utilized for their capacity to identify complex attack patterns, especially subtle low-rate traffic anomalies that traditional systems might miss. Beyond detection, ML machine learning extends its utility to traffic classification, crucial for robust security measures against DDoS attacks, with some techniques reaching up to 97.49% accuracy in detection, according to some of the research we reviewed. The main network SDN responsible of waking Dawn's SDN plays a crucial part in our system. We harness its expansive visibility to detect secure inconsistencies. The integration of machine learning with the main SDN optimizes our real-time network flow and allows Dawn to be more intelligent without affecting its efficiency. The central SDN controller is instrumental in network management in the Dawn network's regular operation. It monitors the network's status and issues IP tables to the switches, acting as the network's brain. The SDN orchestrates traffic flow, while the switches carry out SDN commands by directing traffic to the target servers. Here in this picture, you can see a normal traffic between an SDN target servers and its switches. During the attack, our workflow is initiated. As you can see, Dawn has been alerted in purple. The initial setup: configure the main SDN for communication with Dawn switches. Initialize Dawn SDN with necessary configurations. Establish preprocessors and their communication channels. Ready the ML module for anomaly detection based on traffic analysis. If you're looking at the graph figure over here, you can see the legend for logic and for error. As I continue, operational workflow: main SDN assesses incoming packets for normal processing or redirection to Dawn switches. For load balancing, main SDN evenly distributes packets among Dawn switches. Dawn SDN manages system status, activating or deactivating based on network load. Dawn SDN updates and sends forwarding tables to switches according to its load balancing algorithm. Dawn switches route packets to preprocessors. Preprocessors filter and secure packets, updating Dawn SDN with new blacklist, whitelist data. Dawn SDN compiles comprehensive lists, sharing them with all preprocessors and the main SDN. Safe packets are forwarded to their destination. The ML module in main SDN adapts security measures based on continuous learning from network traffic and Dawn data. Preprocessors are dynamically activated for traffic analysis. Urgent no load balancing is initiating during critical threats, with preprocessors balancing load amongst themselves if Dawn SDN fails. Continuous monitoring and logging are maintained for network performance and security. As for the shutdown procedure, the main SDN signals Dawn SDN to deactivate unnecessary components when system load decreases. Main SDN reroutes traffic away from Dawn switches to the main network. Dawn SDN shuts down preprocessors and switches. Main SDN archives Dawn's whitelist, blacklist for future reference and ML analysis. Dawn's defense strategy emphasizes load balancing to combat DDoS attacks, distributing traffic across servers to prevent overloads. This fusion of software-defined networking with network functions virtualization offers for efficient traffic management and real-time malicious traffic detection. To showcase its base model, we've simulated its load distribution logic at the GitHub link right here. Dawn's load balancing algorithm operates systemically. On a packet's arrival, it prioritizes directing it to an available virtual preprocessor. If none are available, a physical preprocessor is sought. In the event that both options are exhausted, a new physical preprocessor is instantiated. This method ensures efficient resource utilization, preventing choke points, and optimizing packet flow to maintain the network's smooth functioning. However, what happens when things don't go as planned? In the event of SDN failures, Dawn has a built-in safety net. As we mentioned, it falls back on its preprocessor's innate load balancing abilities. This ensures that services remain uninterrupted and operational even during challenges. Dawn SDN defenses. After being initialized by the main network SDN, Dawn SDN activates upon receiving the threat notification. It receives a list of previous attacks, black and white list, as well as data from the main SDN's machine learning analysis. For traffic management, it whitelists, prioritizes traffic from verified sources, and sets Dawn switches with appropriate IP tables to send to the working preprocessors. Blacklisting, it denies access to known malicious entities to mitigate threats and sends updated blacklists to the main SDN for further ML, as well as for added security at the main network's own edge by updating its own IP tables. As for Dawn SDN, it also does rate limiting and modulates incoming traffic to prevent network overload during DDoS attack. As for anomaly detection, it monitors traffic pattern for inconsistencies, utilizes advanced machine learning techniques like traffic intrusion detection for deeper analysis. It is in constant communication between the preprocessors, its switches, and the main SDN, regularly updating network-wide whitelist and blacklist for enhanced security responses. For Dawn preprocessor defense, after the load balancing algorithm decides on the number of preprocessors to activate, each preprocessor will receive packets from Dawn's switches as well as receive black and white lists from Dawn's SDN. And furthermore, after inspection, updated lists by each preprocessors are sent back to Dawn SDN to merge and update the shared list back to the preprocessors themselves and to the main SDN. As part of the preprocessor's defense, signature-based detection function scans packets against the list of malicious signatures for immediate threat neutralization. For anomaly detection, it identifies abnormal traffic behavior. For protocol verification, it detects malicious activities such as SYN flood attacks by analyzing protocol adherence. At the firewall level, a robust defense is provided, quickly filtering out flagged content. For deep packet inspection, it offers detailed packet content investigation, ensuring thorough scrutiny. For behavioral analysis, it assesses traffic volume, frequency, and patterns to identify potential threats not matching known signature. Because of the programmability within SDNs and NFVs, we can create much more robust defense algorithms and implement those softwares as we see fit. This is just a sample. Setup. So for the setup, we have components. For hardware components, these are the pillars of Dawn. The Dawn system is structured around three main hardwares: Dawn switches, Dawn SDN controllers, and preprocessor servers. Each serves a distinct yet interconnected role in ensuring network resilience against DDoS threats. Upon some research, the following hardware stood out. For Dawn switches, in order to direct traffic efficiently and securely, we selected the Cisco Nexus 9000 series for their remarkable data handling capabilities, offering high throughput and low latency, crucial for managing DDoS scenarios. These switches stand out for their advanced security features, energy efficiency, and unparalleled scalability, making them an ideal choice for Dawn's architecture. For SDN controller hardware, we've opted for the Lenovo ThinkSystem SR950 servers. Their robust processing power and expansive memory capacity are tailored for intricate network operations characteristic of 5G environments. Dawn's need for high-speed networking interfaces, scalable storage, and virtualization support are met with the ThinkSystem server, ensuring comprehensive management and robust security. Preprocessor servers, which are tasked with initial data analysis and filtration, our selection leans towards the Dell PowerEdge R740 series, chosen for their balance of performance and cost effectiveness. These servers are equipped with Intel Xeon Gold preprocessors and ample RAM, ensuring swift and accurate preprocessing tasks critical for Dawn's operational efficiency. For Dawn's intelligence and software components, we have options for Dawn's for the SDN control. We have Open Daylight and ONUS, both offering unparalleled flexibility and a rich feature for network management. We also have HA Proxy and Nginx, which serve as our choices for load balancing, critical for handling high traffic volumes. The integration of NFV solutions could be done with the likes of OpenStack, Tracker, and OpenNFV. There are many more software and hardware available that we would need. However, these are just the core components. For deployment, Dawn as an integrative solution, Dawn is designed to integrate with existing security infrastructure, enhancing DDoS defenses with its advanced machine learning and 5G specific threat detection. This capability allows organizations to adopt Dawn without discarding their current security systems, providing a complementary layer that fills gaps, especially in the rapidly evolving 5G security landscape. Dawn as a standalone defender for new infrastructure or businesses seeking a comprehensive DDoS solution, Dawn stands out as a robust standalone system. It excels in traffic analysis, real-time monitoring, and adaptability, offering powerful protection, particularly for high-risk servers requiring constant uptime, which is what we designed it for, to protect those very valuable servers. Dawn's scalable nature ensures it meets the needs of various businesses, sizes, and traffic volumes. The configurations for standalone Dawn system. So for high intensity setup for severe DDoS defense, for switches, we chose the Cisco Nexus 9800 series. For high traffic volume, the SDN controller Lenovo ThinkSystem 950, as we talked, and the Dell PowerEdge R740. However, for the low intensity, we switched. The only change we did was for the Nexus, instead of 9800, we chose the 9300. So for cost analysis, high intensity configuration costs range from approximately from 1.8 million to 10.16 million, catering to severe DDoS threats. Low intensity setups estimate between 127,000 US dollars to 196,000. Designed for environments with moderate DDoS attack risk. The Dawn system, whether integrated into an existing framework or deployed as a standalone solution, can offer flexible, scalable defense mechanisms against DDoS attacks. So as for challenges in implementing Dawn, they are technological integration. Combining various technologies within Dawn requires overcoming compatibility issues through extensive testing. Also, we face economic investment difficulties, and initial setup cost may be high, but the value and potential cost reduction over time justifies the investment in Dawn. And Dawn's scalable design allows adaptation to various organizational sizes and budgets. As for our future direction, with technological advancements, we must embrace new technologies such as AI. So upon revision later on, we might have to think about that. And whatever new technologies come up, we will always make sure to try to include them and always be dynamic and resilient. Thank you so much.